Hello, in this video I'm going to talk about the Hertzsprung-Russell diagram, usually referred to as the HR diagram, which is very famous in astronomy. And it was a major step forward in understanding stellar evolution, the life cycle of stars, and showing that there's a clear set of processes that are undertaken inside stars. It's not just a sort of random free-for-all. This was unlocking what is actually going on. So how did this all come about then? Well, you got Hertzsprung and Russell, two astronomers who were working independently. Hertzsprung was Danish, Russell was American, and they were both working in the early part of the 20th century. And in this sort of period from 1910 to 1915, they were both putting together this relationship between luminosity and temperature for stars. And that wasn't easy to do. I mean, we've been discussing this in the previous videos, that working out the luminosity of a star is very difficult because you need to know how far away it is. It could be that a star is really bright, as it might look in the sky, but it could be that it's just very close to us. So unless you know how far away it is, it's hard to say how luminous it is. Temperature has got its own challenges as well. We can see that there are blue stars, red stars, for hot stars and cool stars. We can look at stellar spectra. We can get an idea. It's a bit easier with temperature than it is with luminosity, but there's still issues there for actually calibrating all of this stuff. And people have been surveying stars, thousands of stars throughout the 19th century, and they were looking for these patterns. We've already seen one of the patterns when we were looking at stellar classification, looking at those hydrogen absorption lines and how prominent they are in stellar spectra, and that was what was given those letter classifications, what they started off in alphabetical order, going from strong hydrogen absorption lines down the alphabet to weaker ones. Okay, these letters have been rearranged in our stellar classifications now in our one big apple flattens giant killer monkey. But the A and B type stars here at the hot end of our stellar classifications, these are the ones that have got the strong hydrogen absorption lines. So a lot of people were looking for patterns, but Hertzsprung and Russell were the ones who cracked it with luminosity and temperature. So the diagram that they came up with, and this is still, you see variations on a theme, but things haven't really changed. We've got on the x-axis, we've got some measure of temperature. Now that could be temperature itself, in which case we're doing the log of temperature here on the x-axis, and it runs right to left rather than left to right. So we're going low temperature on the right hand side up to high temperature on the left hand side. So we've got low to high going on here for temperature. Now we could substitute, get rid of temperature and sub in spectral class. We could go M and O. These letters here, our 7 letters, well, the O are the high temperature stars and the M are the lower temperature stars. So we've got different ways we can actually scale this x-axis. Now on the y-axis, we've now got luminosity. Again, we usually have the log of luminosity. Sometimes they don't put it on log scale. Well, they'll have a log scale, but they don't actually specify it in log values. So if you're actually going to be doing, so we've got luminosity here. So if you're going to do the log of the luminosity divided by the luminosity of the sun, then you'll be going from about -4 at the bottom up to 5 at the top. So you're always going to get essentially a log scale, but sometimes this would be written out, rather than having 5 at the top, you'll have 100,000. So they don't put it actually as a log number. They don't take their 10 to the 5. They're going to write and change that to be 5 once you've taken a log of it. They're going to actually put out the 100,000, but it's still a log scale. You don't have a linear scale there. But we got luminosity going low to high on the y-axis. Again, it might not be luminosity that they actually show. They could have absolute magnitude on here. We spoke about absolute magnitude in the previous video, and that is another way of measuring the luminosity. How bright does a star look if it's put at a distance of 10 parsecs away? So you're putting all of the stars at the same distance, saying, well, how bright do they then look at that distance if they're all at 10 parsecs? Well, of course, that is also going to be a measure of luminosity. So we might have absolute magnitude on the y-axis. But either way, we've got power output in our watts is going up on the y-axis, and our temperature, our Kelvin, is going on the x-axis. So Hertzsprung and Russell, they were working on this and trying to find a relationship, and they both had different ways of working around the distance problem. So for Hertzsprung, he noticed that stellar spectra that have got very narrow spectral lines tend to be further away. So he was using that as his sort of general broad brush guide for working out distances and then working out the luminosity. And he also looked a lot at star clusters. And so, well, if they're all at the same distance because they're in the same star cluster, then I can start looking at relative luminosity amongst those. So he had his way of doing it. Russell was picking nearby stars, or again, clusters of stars. So, okay, for nearby stars, we can use parallax methods and things like that. In clusters, you've got something called the moving cluster method as well, which allows you to work out distance. And then they were using this proxy of spectral classification for temperature. And the upshot of it, when they started plotting stuff out, they weren't just getting, someone might think when this hadn't been done before, you've got these axes and you're just going to get some random distribution. You put all the dots on and it just comes out all over the place. But they saw a very definite pattern. So you had this central sort of curve going on, something like this, with a branch going up here. Then you had a whole load up the top and a little collection down the bottom. So they were clustered. And okay, you've got, these are areas rather than just straight lines. So you've got this sort of, central area here where you're seeing a lot of stars. Then this branch here has some stars, an area up the top. So it's areas rather than just lines. But the stars were mostly falling into these regions, particularly this bit here. This central curve bit, what's referred to as the main sequence, was particularly densely populated with stars. And it was quite interesting where they were located. I mean, they stuck, just to put a few stars that we know of on here, the sun is around about here somewhere. So, at the cool end of the x-axis. Obviously, when it comes to doing the luminosity, it's going to be in the middle. We're measuring these luminosities relative to the sun. So the sun is around about there. You have Betelgeuse sort of around about here, so cool but very luminous. So that would be Betelgeuse. We spoke about Rigel in previous videos. So we're getting higher temperature, very luminous. So you might be around about here somewhere. So these are the sort of locations you're getting. And people, they were starting to think, okay, this is interesting. There's clearly something going on. People didn't know what. And we're going back to the 1910s. I mean, people didn't even know what a star was back then. There was no knowledge that it was nuclear fusion that was powering these stars when you're back in 1910. So that wasn't on the table. But so people knew something was happening. They knew there was something to explain in all of this. They just didn't really know what. Now, in the 1920s, you had an English astronomer called Arthur Eddington, and he anticipated the discovery of nuclear fusion in stars, which then happened in the 30s and 40s. And it was that combination of thinking, right, okay, we've got these nuclear processes going on in stars. We've got this distribution of stars in terms of the relationship between luminosity and temperature. How can we then build that all in to a unified, coherent theory of stellar evolution? Now, I'm going to go through that description in the next video. I'm not going to include it all in here. But they were explaining, well, how does each star get to where it is on the diagram? Why is it there? Why are they moving around? Because this was what the theory was explaining, that stars move around this diagram. So they might start off here in the main sequence. So with the sun, let's take the sun then. So it starts off at this relatively standard, unexceptional star at a fairly middling temperature, fairly middling luminosity. but then the sun will evolve into, this is where giants are. So this branch that is coming off the side here, this is moving into giants. So you've got this sort of cluster of them. So not where I've actually written the word giants, but sort of at the end of this branch here. So it's a path that the sun will be taking off of the main sequence up to, let's put an arrow in red so you might be able to see it, up here into this giant branch. It will then progress from being in that branch with the giants. It will then move over in its life over to the top end of main sequence, and then down here where we got the white dwarfs. So this little bunch of stars at the bottom are white dwarfs. So they're not very luminous because they're so small, but they're very, very hot. These are the cores of stars at the end of their life. So stars that aren't massive enough to have gone supernova, but they end up being white dwarfs. So there's this process that's going on for these main sequence stars where they spend their life on the main sequence, they move along the main sequence up to giants, pass across the top end of main sequence, and then down to white dwarfs. Now, of course, we can't actually watch stars doing this because it takes billions of years for stars to actually go through their lifespan. But the theory that was built for stellar evolution fits in with the Hertzsprung-Russell diagram and explains why stars of certain types and appearances are where they are on the diagram. You've got a similar explanation for what's going up the top here. So these are the supergiants. We've already been looking at Rigel and Betelgeuse as being supergiants. Remember that in our stellar classification again, when we were going through the spectral classes and such like. Now, supergiants, they will move from left to right across here. So they will expand and cool. So think of our luminosity, our Stefan's law. We got our 4 pi r squared Stefan-Boltzmann constant times t to the 4. So if they're going to be staying at the same luminosity, then the temperature is dropping, but the radius is increasing. And then when they get to the far end here, eventually they'll go supernova. So they're starting on the left. They are getting through their life cycle relatively quickly. Again, I'll go through this in detail in the next video. But they're going to be cooling, they're going to be expanding, and then they're going to go supernova. So this really was setting up the whole framework for explaining stellar evolution. So that's why it was so groundbreaking. I mean, it's still really useful nowadays because you can look at stars, look at their spectral classification, get some idea of luminosity, and then place them somewhere on the HR diagram, which will tell you a bit about where they are in their life cycle. You can do main sequence fitting, this sort of thing. If you've got something that looks a bit like the sun, then it's going to be in a certain place on the main sequence. You've got some kind of idea about where it is in its life. Now, it's not always easy to do that. As I think I briefly mentioned in a previous video, you can get things like white dwarfs, which in some situations can look very similar to your super luminous, very your ultra hot supergiants, your Wolf-Rayet stars, because we don't have full access to the stellar spectra for these super hot stars, because a lot of the interesting bits cut out by the Earth's atmosphere. But still, it's giving that framework for telling a story. So that's what you're looking at on the Hertzsprung-Russell diagram. Don't get caught out by the x-axis going with high temperature on the left and low temperature on the right. So the x-axis going in the opposite direction to normal. Get used to the fact these are log scales. Get used to the fact that you can have different ways of talking about the temperature or the luminosity. So you'll see different things on the x and y axis, but they're all telling the same story. So that's the important part. Get familiar with the variations on the axes, but really you want to be familiar about the story. And I'll talk about that in the next video.